Welcome to my 30th tutoring session in A-level chemistry. In this video, I'll talk about intermolecular forces. It is a part 2 video of the 5-part series. Please take a moment to watch the part 1 video discussing the types of chemical bonding. Link to the video is given in the description below. Please do watch the video. Don't forget to subscribe my channel, share, like, comment and watch the full video. In this session, I'll briefly explain the ion-ion, ion-dipole interaction, dipole-dipole interaction, hydrogen bonding, and van der Waals forces. There are two types of forces, intermolecular forces and intramolecular force. Intermolecular force or bonds or intermolecular interactions occur between molecules. It is represented by dotted line between the molecules. An intermolecular force is a weak bond that occurs between molecules. While on the other side, intramolecular forces are the strong forces that hold the atoms together within a molecule. Intermolecular force is denoted by a solid line joining the atoms together that are held together by covalent bond. Now, intramolecular forces are strong bonds between atoms within a molecule. That is shown by a solid line joining the two atoms held together by covalent bond. Now, intermolecular forces occurs between polar molecules like hydrogen fluoride and non-polar molecules like alkanes, and it is denoted by dotted line. In this video, I'll give a brief explanation about the intermolecular forces or intermolecular interactions. Now, intermolecular forces, it can occur between non-polar molecules like alkanes or polar molecules like hydrogen fluoride molecules. There are three types of intermolecular forces: van der Waals force, hydrogen bonding, and dipole-dipole interaction. Now, van der Waals forces are present in all molecules regardless of the polarity, and they occur between non-polar atoms like noble gases, and they also occur between non-polar molecules like diatomic molecules, for example halogens. And van der Waals forces are particularly significant in non-polar molecules like alkanes. A second type of intermolecular force is hydrogen bonding. Hydrogen bonding occurs between hydrogen atom and electronegative atoms like oxygen, nitrogen, and fluorine. Let me explain the concept of hydrogen bonding with respect to these three scenarios. In the first scenario, hydrogen atom is covalently bonded to oxygen atom in a water molecule, interacting with electronegative oxygen atom of another water molecule. In the second scenario, hydrogen atom covalently bonded to oxygen atom in a water molecule interacts with the electronegative nitrogen atom of another molecule. In the third scenario, you find hydrogen atom is covalently bonded to fluorine atom that interacts with electronegative fluorine atom of another hydrogen fluoride molecule. So with these three scenarios, what we understand is that hydrogen bonding takes place only when the hydrogen atom is covalently bonded to an electronegative atom, and only then it will interact with the electronegative atom of another molecule. And hydrogen bonding plays a vital role in several chemical and physiological or biological processes. The third type of intermolecular force is dipole-dipole interactions. Now, dipole-dipole interaction occurs between polar molecules where the positive end of one molecule attracts the negative end of another molecule. Dipole-dipole interaction is present in molecules with permanent dipoles due to difference in electronegativity between the atoms. Now, in case of acetone molecule, the electronegativity of oxygen atom is greater than that of the carbon atom. As a result, the highly electronegative oxygen atom attracts or pulls the shared pair of electron closer to itself, and in the process develops a partial negative charge, while the carbon atom develops a partial positive charge. So now the carbonyl group of the acetone molecule has a positive end and a negative end. It has a dipole with a polar covalent bond. Now I included the ion-ion and ion-dipole interaction in order to have a comparative assessment of the strength of the intermolecular forces. Oppositely charged ions are attracted to each other due to electrostatic force, that is F, and this is indicated by dotted line, where Q1 is the magnitude of the positive charge, Q2 is the magnitude of the negative charge, and R is the distance between the center of the two ions. Now, the electrostatic force of attraction between the oppositely charged ions is described by Coulomb's law, which states that the electrostatic force of attraction between the oppositely charged ions is directly proportional to the product of charges and inversely proportional to the square of distance between the ions. Where F is the electrostatic force of attraction between the oppositely charged ions, K is the Coulomb's constant, Q1 is the magnitude of charge of positive ion, Q2 is the magnitude of charge of negative ion, R is the distance between the center of the two ions. Now, as the distance R between the two ions reduces, the electrostatic force of attraction between the oppositely charged ions increases, and it is this strong electrostatic force of attraction between the oppositely charged ions that holds the ions together, and this leads to a network of ions. So what you see here is a network of sodium and chloride ions held together in the crystal lattice of common salt sodium chloride. Now here is the unit cell of the sodium chloride crystal, and in unit cell you will find the negatively charged chloride ion surrounded by positively charged sodium ion, and the positively charged sodium ion is surrounded by negatively charged chloride ion. And there are several unit cells that are stacked together that results in the overall crystal lattice structure of sodium chloride, and it is in the shape of a cube. So sodium chloride has a high melting point of around 800 degrees Celsius, and this shows the strength of the bond between the opposite charged ions. So this is an example of ion-ion interaction. So I explained the ion-ion interaction with respect to the sodium chloride, and it's a very strong force of attraction. Now, when sodium chloride salt is added to water, it dissolves completely. And why it dissolves completely in water? Let me explain. Now, water is a polar solvent. It has a positive end and a negative end. It has a dipole with a polar covalent bond. And this is a symbolic representation of water molecule. So when sodium chloride is added to water, it dissolves completely. And what actually happens is that the positive end of the water molecule attracts the negatively charged chloride ion, while the negative end of the water molecule attracts the positively charged sodium ion. And you can see layers of water surrounding the sodium ion and the chloride ion. So you can see it as a hydration sphere. So it is the layers of water molecules or the hydration sphere that prevents the sodium ion and the chloride ion from joining together. So there is an insulation around the sodium and chloride ion. So what you see here is hydration sphere around the sodium ion and hydration sphere around the chloride ion. So this is an example of ion-dipole interaction where you find the interaction between the sodium ion and the water molecules, chloride ion and the water molecules. So though the ion-dipole interaction is strong, but is weaker in comparison to the ion-ion interaction. Now moving on to the hydrogen bonding. The first example, the hydrogen atom is covalently bonded to oxygen atom, which interacts with the electronegative oxygen atom of another water molecule. In the second example, hydrogen atom covalently bonded to the oxygen atom of methanol molecule interacts with the oxygen atom of another water molecule, which is electronegative in nature. In third example, hydrogen atom covalently bonded to oxygen atom of a water molecule interacts with electronegative oxygen atom of dimethyl ether. Fourth example, hydrogen atom covalently bonded to oxygen atom interacts with electronegative oxygen atom of acetone molecule. Fifth example, hydrogen atom covalently bonded to fluorine atom interacts with electronegative fluorine atom of another hydrogen fluoride molecule. So all these 5 examples summed up together are examples of molecules held together by hydrogen bonding, and it's a special type of dipole-dipole interaction. So hydrogen bonding is a special type of dipole-dipole interaction where the hydrogen atom is covalently bonded to a electronegative atom interacting with the electronegative atom of another molecule. So what about interaction between the two acetone molecules? So the interaction between the two acetone molecules is a pure example of dipole-dipole interaction. So here nowhere you find the participation of hydrogen atom in the interaction, and therefore it will not be a hydrogen bonding. So hydrogen bonding involves the active participation of hydrogen atom that is covalently bonded to an oxygen atom. So what you find here is interaction between two polar molecules, acetone molecules, where the positive end of one molecule attracts the negative end of another molecule, which I have already explained. So hydrogen bonding is stronger in comparison to the simple dipole-dipole interaction. So dipole-dipole interaction is weaker than the hydrogen bonding. Now moving on to the van der Waals force. Now van der Waals force is also called as London dispersion force. So it is a weak force that occurs between non-polar molecules and non-polar atoms. So you can find the van der Waals force between the non-polar noble gases like helium, neon, argon, krypton and xenon, and between non-polar molecules like diatomic halogens like fluorine, chlorine, bromine and iodine. Now van der Waals force is particularly significant in non-polar molecules like alkanes. Now temporal dipoles can occur in non-polar atoms or molecules, which induces a dipole in neighboring atoms or molecules. Now let me explain the mechanism of van der Waals force with respect to the non-polar noble gas atom, which is monoatomic in nature. So let me explain it with respect to the monoatomic noble gas helium. Now helium has 2 protons in the nucleus and 2 electrons in the outermost shell. Now electrons are always in constant motion. And as a result, there is a temporary or momentary unsymmetrical distribution of electrons, and this leads to development of dipole in the atom or the molecule. Now, once the dipole is formed, you find the electron density is more on one side of the molecule as compared to the other end. Now, the electrons on the one end of the molecule, it tends to repel the electrons present in the outermost shell of the neighboring neutral helium atom. And this inter-electronic repulsion between the two helium atoms induces a dipole in the neighboring neutral atom B. So now you have got helium atom B with a dipole and helium atom A with dipole. So you have got two atoms with dipoles and they attract to each other, and this attraction forces the two atoms to come close together because of the positive and negative ends attract each other. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.